In this video, we're computing the energy released by an asteroid falling to the surface of the Earth from a large distance. And the way we're going to approach this is to actually just compute a raw work integral for the work done by gravity. I just recently gave this on a quiz in one of my physics courses, and we didn't have potential energy yet. We just defined work as an integral. So if you like, you could redo this problem with the expression for gravitational potential energy when r varies over a large distance. But keep in mind that potential energy really is just a bookkeeping device for computing the work done by a conservative force like gravity. So we're going to compute the work done by gravity as this asteroid falls from a great distance to the surface of the Earth. And of course, that work would be transformed into the kinetic energy of the asteroid when it impacts the surface of the Earth. So after finding a symbolic expression for the total work done by gravity, we're going to plug in some numbers here. We have big G for Newton's law of gravitation, the mass of the Earth, the radius of the Earth, because that's the final radius of the asteroid, and then the approximate mass of the asteroid, which was obtained by assuming a 1 kilometer diameter and an average density of 2,500 kilograms per cubic meter for the rock. Finally, we're going to express our answer as a multiple of the approximate energy output of the little boy atomic bomb that was dropped on Hiroshima in World War II. So we're told that energy output was about 63 terajoules, or 63 trillion joules. So we'll get started with just a quick reminder of how work is computed as an integral. So we say the work done by gravity is the integral of F dotted into dr. And we compute this integral as r goes from some initial value to some final value. So r initial to r final. Now that force is the force of gravity exerted by the Earth on the asteroid. And I'll just call that Fg for the force of gravity. And as this asteroid falls, we have incremental changes in the position vector. Those are the drs. So every small contribution to the work done by gravity here is positive because the force of gravity points in exactly the same direction as the vector dr. And that's going to be really important to keep in mind because we run into a very subtle notational difficulty in this problem, and it's going to require correcting a minus sign. So we keep setting up our integral. In our initial value of r, we're saying that the asteroid was initially very far away, so we're going to put an infinity in there. And then our final value of r is the radius of the Earth. That's the distance from the center of the Earth when the asteroid impacts the surface. Now, when the separation distance is just some arbitrary value, little r, the force of gravity is given by Newton's law of gravitation as g times the product of the two masses here. So we have the mass of the Earth and the mass of the asteroid divided by the separation distance between them squared, so little r squared. And then we have the magnitude of our little dr vector, which is just dr as a scalar. So now we can just go ahead and compute this integral, noting that g and the two masses are both constants. And when we find the antiderivative of 1 over r squared, that's a negative 1 over r. And we have to evaluate this thing from infinity to our Earth. First, I want to address the infinity issue. Provided there's no ambiguity caused by subbing in r equals infinity, that's a perfectly valid approach to evaluating this limit. So if I sub in r equals infinity, 1 divided by infinity is unambiguously 0. So subbing in that limit gives me a 0. Subbing in the upper limit, we discover our minus sign problem. I end up with negative 1 over r Earth for that term. So our work done by gravity simplifies to g, mass of the Earth, mass of the asteroid, over the radius of the Earth, but with a minus sign in front. And then we're going, wait a second. I know for sure this work is positive because I can see that the force of gravity exerted on this asteroid is always in exactly the same direction as the displacement vector. That's a guarantee that we should have a positive work done by gravity, and that positive work, of course, resulting in an increase in kinetic energy. So the question is, where is the minus sign hiding in our calculation? And this is actually a really common occurrence when we set up integrals in gravitation and electrostatics. You have to be really careful if you set up an integral with a decreasing separation distance like this, because this dr in the integral is actually hiding a minus sign. And this goes back to the definition of an integral as a Riemann sum. If we go from a large r to a small r in our limits of integration, that means r is getting smaller, which means dr is actually a negative increment of r. And this is where our minus sign is coming from. And this is why when we set up integrals like this in gravitation and electrostatics, we normally avoid this issue by choosing an integration path that gives us an increasing value of r. But for this particular problem, it just didn't make sense to reverse the direction of the process since we're just directly computing a work integral on this particular path. So the bottom line is, we're absolutely convinced that the work is positive because the force always points in the same direction as the displacement. We have a sense for where the minus sign is hiding. And so we're justified in just forgetting about the minus sign here, and I'm going to write that the work done by gravity is given by g, mass of the Earth, mass of the asteroid, divided by the radius of the Earth. All right, so gravity has been tugging on this asteroid and speeding it up all the way down to the surface of the Earth, and this is how much work was done. And now we can get a number on exactly how much energy transfer this represents. So we start with our approximate value for big G, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And the mass of the Earth, 5.97 times 10 to the 24th kilograms. And the approximate mass of a 1 kilometer diameter asteroid, 1.3 times 10 to the 12th kilograms. And then we divide by the radius of the Earth. And this was given to us in some unusual units. We were given a radius of the Earth of 6,371 kilometers. So I'm just going to write that in expanded form in meters because that's the SI base unit here. So we need to tack on 3 zeros. So this is 6,371,000 meters. And when we run the numbers on this to 3 significant digits, we end up with 8.13 times 10 to the 19 joules of energy released. Now, what about the equivalent of this energy release in terms of atomic bombs? We're going to take our total energy released in this asteroid impact, 8.13 times 10 to the 19 joules, and then divide by the energy released in this Hiroshima atomic bomb explosion. That was given to us as about 63 terajoules, a number that I got from Wikipedia, by the way. And tera means trillion. That's 10 to the 12th joules. And when we run the numbers on this and just round to 3 significant digits, we get 1.29 times 10 to the 6th bombs. So that's 1.3 million nuclear bombs going off all at once on one spot on the surface of the Earth. And I think this does a good job of explaining why scientists like Carl Sagan and Neil deGrasse Tyson put asteroid impacts on the short list of existential threats to humanity. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.